Welcome back to the ninth installment of my series on Earth's extinction events. Today, we're diving into the world's recovery after the mass extinction that ended the Cretaceous period, the catastrophic event that wiped out the dinosaurs. But the story of recovery wasn't simple. The survivors faced their own challenges, especially with a wildly fluctuating climate shaping their fate. If you're new to this series, don't worry, this video stands on its own. But if you're curious about earlier mass extinctions, check out the full playlist. If you'd like to dig deeper, I've linked a document in the description with all the sources and image credits used in this episode. Before we get into the details of recovery, let's set the stage. The Palaeogene period lasted from 66 to 23 million years ago, kicking off the Cenozoic era and stretching across 43 million years. That's a long time during which the Earth's ecosystems dramatically changed and evolved following the extinction. As we edge closer to the present, geologists start using smaller chunks of time called epochs instead of just big periods. So, while previous eras leaned heavily on periods like the Cretaceous or Permian, and the Cenozoic does still have periods, it's more common now to break the Cenozoic down into its epochs. The Palaeogene had three: the Palaeocene, Eocene, and Oligocene. Why the change? It's because the fossils we find from this era are more precisely dated, giving us clearer timelines. Basically, recency bias in action. The continents during the Palaeogene looked a lot like today's map, with recognizable landmasses like Africa, Eurasia, and the Americas. But there were important differences, like the fact that the land bridge between North and South America wasn't there yet, a detail that would influence climate and biodiversity in surprising ways. The climate itself was a roller coaster. Right after the asteroid impact, Earth was plunged into an impact winter, but eventually things calmed down to a cool, dry climate similar to the late Cretaceous. Then, at the end of the Paleocene, Earth experienced a sudden and dramatic spike in temperatures during what's called the Palaeocene-Eocene thermal maximum, the last really warm period Earth has seen. Temperatures stayed warm through the Eocene, but with the arrival of the Oligocene they dropped again. And for the first time since the Permian, permanent ice sheets formed at the poles. With about 75% of species wiped out at the end of the Cretaceous, huge ecological niches opened up. This triggered a process called adaptive radiation. Surviving species rapidly diversified to fill new roles. This happened fastest in the tropics, but it was a global phenomenon, starting in the Paleocene. Mammals, which had been small nocturnal generalists during the Cretaceous, suddenly took the spotlight. They seized this opportunity and became the dominant group during the Cenozoic. By the end of the Eocene, most modern mammal groups had appeared. Primates, horses, deer, whales, cats, dogs, rodents, rabbits, bats, many of which grew larger than any of their modern descendants. Not only did mammals occupy new niches, but they also explored environments that had never before seen mammals. Bats took to the skies, and whales dove into the oceans. The only surviving dinosaurs, birds, also flourished. With pterosaurs gone, birds ruled the skies, although bats would soon compete for that aerial real estate. Birds weren't limited to flying either. Some evolved into flightless forms that filled the niches left by extinct dinosaurs. Think penguins, ratites, and terror birds. Plants transformed as well. Ferns dominated just after the extinction, but over time, more modern groups like grasses and herbs rose to prominence, especially as the planet cooled during the Oligocene. Conifer forests took hold in mountainous regions where flowering plants struggled. In the oceans, ray-finned fish exploded in diversity, especially in open waters. Coral reef fish, like seahorses and clownfish, first appeared and began to diversify, shaping marine ecosystems as we know them today. We've already touched on two major climate events of the Paleogene, but both are linked to extinctions and ecological turnover, so let's explore them more thoroughly. The first is the Palaeocene-Eocene thermal maximum, or PETM for short. This event happened about 56 million years ago, and was a brief but intense global temperature spike, lasting roughly 200,000 years. The PETM marks the boundary between the Paleocene and Eocene epochs. During this time, global temperatures jumped by about 5 to 8 degrees Celsius. That's like 9 to 14 degrees Fahrenheit. This rapid warming was driven by a huge increase in atmospheric carbon, like in the form of carbon dioxide or methane. But here's the kicker. No one really knows what triggered this massive carbon release, although there are several theories. One piece of the puzzle lies in the weird shift in carbon isotopes. Carbon comes in two common forms or isotopes, carbon-12 and carbon-13. Normally, the ratio between these two is stable, but during the PETM, carbon-13 dropped dramatically relative to carbon-12. This isotope signature helps rule out some causes while keeping others on the table. Understanding the Earth's geography helps too. At this point, the Panama Isthmus hadn't formed, so the Pacific and Atlantic Oceans flowed directly into each other near the tropics. South America was still connected to Antarctica, preventing its full isolation. These oceanic connections played a role in how heat and carbon circulated during the PETM. Pinning down the exact cause of the PETM is tough. Temperatures were already rising before the PETM, so it's possible the event pushed Earth past the climate tipping point. But what triggered the push? Volcanic activity is a prime suspect. Around 56 million years ago, a cluster of volcanic vents appeared in northern Canada, and volcanic eruptions release massive amounts of carbon dioxide. Another volcanic source could be the North Atlantic Large Igneous Province, where elevated mercury and osmium levels suggest significant eruptions took place, releasing methane and carbon dioxide. Some have even suggested meteor impacts. While impact signatures exist from this era, like debris off New Jersey's coast or ejecta in the Atlantic Ocean, no definitive giant impact crater has ever been confirmed to explain the PETM. Methane release from ocean floor methane hydrates is another idea. As temperatures rise, methane trapped in these ice-like deposits could destabilize, releasing greenhouse gases in a feedback loop. This hypothesis remains debated with no firm consensus. Other theories, like carbon from burning peat bogs or periodic climate cycles linked to Earth's orbit, have been proposed but lack strong evidence or have been debunked. So what caused it? In short, no one knows for sure. Volcanism and meteors are the leading candidates, but it's still largely speculation. While the cause remains a mystery, we do understand what happened next. The warming boosted evaporation, causing more rainfall and a generally wetter climate. The oceans, especially the Arctic, became less salty as rainfall and runoff increased. The PETM also triggered the only known anoxic event where the oceans lose oxygen in the entire Cenozoic. This was rare compared to earlier extinction events, but it had big impacts on marine life. Sea levels fluctuated wildly, rising by as much as 20 to 50 meters, or 65 to 160 feet in some areas, because of melting ice and increased rainfall. Ocean acidification was severe. The ocean's pH dropped by nearly half a unit, roughly the difference in acidity between lemon juice and Coca-Cola. That subtle change in numbers masked a profound transformation, one that sent shockwaves through marine ecosystems. The worst extinctions were marine. Benthic foraminifera, tiny single-celled seafloor dwellers, lost 35 to 50% of species, their worst mass extinction ever. Why they were hit so hard isn't clear, since they survived other anoxic events better. Corals, sensitive to temperature and chemistry changes, experienced widespread bleaching and reef collapse, especially in the tropics. But the full impact on corals is not well documented, so there is a lot about this extinction that we still don't understand. Other marine invertebrates, like echinoderms, mollusks, and ostracods, faced regional extinctions where anoxia and heat were severe, but didn't experience the global die-off seen among foraminifera and corals. On land, plants saw some turnover from heat and drought, but there were no major extinctions at the genus or family level. Microbial soil colonies may have suffered die-offs, inferred from chemical cues, but this remains speculative due to the poor fossil record. Terrestrial vertebrates and invertebrates actually thrived. The PETM saw the first primates, horses, pigs, and camels, and herbivorous insects exploded in abundance. Reptiles like crocodilians and early boas and pythons expanded their range towards the poles, reaching places like modern Wyoming and the UK. Birds such as the ancestors of parrots and shorebirds also appeared around this time. So, while the PETM was a challenging period for some marine groups, it opened doors for others on land and in the skies. Mobile vertebrates escaped the worst and diversified rapidly. That's probably why the PETM is often overlooked as a mass extinction. It was one, but only for very specific groups, while for many others, it was an era of opportunity and expansion. The warmer period didn't last, and that brings us to the other major event of the Palaeogene Period, the Eocene-Oligocene Transition, or EOT for short. This occurred around 33 to 34 million years ago and marked the beginning of the late Cenozoic Ice Age, an ice age that actually continues to the present day, defined by the presence of large ice sheets in Antarctica. As its name suggests, this new ice age brought a dramatic global cooling. In North America, average temperatures are estimated to have dropped by about 8 degrees Celsius over the course of 400,000 years, a rapid change in geological terms. Several key events, all occurring around the same time, triggered this cooling. One of the main drivers was silicate weathering. The Indian subcontinent had recently collided with Asia, forming the Himalayan mountain range and exposing vast quantities of fresh silicate rock. A similar uplift of the Andes in South America also exposed more silicate-rich material. As these rocks eroded, they reacted with carbonic acid and rainwater to eventually form calcium carbonate. This chemical process removes both carbon dioxide from the atmosphere and acidity from the oceans. Just as rising CO2 levels had driven the spike in temperatures during the Palaeocene-Eocene thermal maximum, its removal now helped usher in a cooler climate. Another major trigger was the opening of the Drake Passage, the body of water between South America and Antarctica. Its formation allowed the establishment of the Antarctic Circumpolar Current, which began circulating cold waters around Antarctica. This isolated the southern continent thermally and helped bring cold, deep waters to the surface, accelerating oceanic cooling. Around the same time, the Tasmanian Gateway, the seaway between Antarctica and Australia, also opened, reinforcing this effect. The formation of the Antarctic ice sheet dramatically increased Earth's albedo, the reflection of sunlight off bright surfaces, further amplifying the cooling. Much of the planet's fresh water became locked up in these expanding ice sheets, which caused global sea levels to drop. As a result, new land bridges formed between continents that had previously been separated. Alternative explanations for the transition, such as meteorite impacts or increased sunspot activity, have been proposed, but there is little to no credible evidence supporting them. These theories can be safely dismissed in favour of the combined effects of silicate weathering, ocean current reorganisation, and feedback from Antarctic glaciation. So, the cause of the Eocene-Oligocene transition seems clear, but what were the changes? The most famous biotic effect of this transition is known as the Grande Coupure, French for Great Break. It refers to a dramatic shift in mammalian biodiversity in Europe, where many native lineages went extinct. Among the better-known groups affected were rodents and primates, but many others, like amphicyonids or bear dogs, paleotheres, early relatives of horses, and creodonts, early carnivorous mammals, also suffered sharp declines. These extinctions were exacerbated by the arrival of Asian species into Europe, made possible by the formation of new land bridges. These Asian migrants included rhinoceratids, early rhinoceroses, entelodonts, sometimes dubbed hell pigs, hyenodonts, early carnivorous mammals, and a variety of artiodactyls and rodents. This turnover stands out as one of the most abrupt and profound biotic changes of the entire Cenozoic. Elsewhere, similar, though less extreme, transitions occurred. In Asia, some native species were replaced by migrants from Europe or North America, driven more by a drying climate than cooling alone. In North America, archaic groups like the Brontotheres, early rhino-like perissodactyls, declined, giving way to more modern artiodactyls, perissodactyls, and carnivorans. These dramatic changes were concentrated in the Northern Hemisphere, where the new land bridges enabled major migrations. In contrast, Southern Hemisphere continents like South America and Australia remained isolated and experienced less disruption. South America, for example, was home to highly endemic groups like notoungulates, marsupials, and xenarthrans, which continued to evolve largely in isolation. While global cooling did influence vegetation and ecosystems there, the biotic impacts were more muted and gradual. Animal turnover was closely linked to shifts in vegetation. As the global climate cooled and became more seasonal, lush tropical forests retreated, particularly at mid to high latitudes. In their place emerged more open environments, temperate woodlands, scrublands, and the earliest forms of grasslands. This shift was especially pronounced in North America and parts of Asia. These new habitats influenced herbivore diversity and distribution, setting the stage for later expansion of grazing animals during the Miocene. The shift in plant communities also had ripple effects on insects, pollinators, and seed dispersers, reshaping entire ecosystems. Discussions of the Eocene-Oligocene transition often focus on mammals, partly because the fossil record is especially rich for them. But other vertebrate groups were also affected. Birds, already diverse and widespread by the Eocene, shifted their ranges in response to changing habitats. Forest-adapted species declined at mid to high latitudes as dense tropical forests vanished. In contrast, birds suited to woodlands and grasslands, such as early owls, songbirds, and ducks, diversified into these new niches. Reptiles also responded to climate change. Crocodiles, for instance, retreated towards the equator, vanishing from temperate regions. While the fossil record is sparse with lizards and snakes, many known Eocene species were tropical or subtropical, suggesting they likely faced similar pressures in local extinctions. Fish were affected both in freshwater and marine environments. In dry regions like Asia, shrinking lakes and rivers led to local extinctions and faunal shifts. In the oceans, colder temperatures and altered currents drove dramatic redistributions. Warm water fish species retreated towards the equator, and those unable to adapt disappeared. Sharks were especially impacted. Many warm water species declined in temperate zones, while cold-adapted sharks diversified to fill the vacated niches. This period saw the rise of several modern shark lineages, including early relatives of great whites, makos, and snaggletooth sharks. Among invertebrates, marine groups were hardest hit. Mollusks like bivalves and gastropods saw extinctions among warm water genera, with many others shifting towards tropical zones. Echinoderms, such as starfish, experienced similar patterns, though deep water species were less affected. Coral reefs contracted and became confined to tropical waters. On land, insect diversity followed changes in vegetation. Forest-adapted insects declined in temperate zones, while generalists and species suited to open habitats diversified and spread. But perhaps the most profound changes occurred not among large animals, but at the base of the marine food web. The onset of Antarctic glaciation and the resulting shift in ocean circulation patterns caused major upheavals in planktonic communities, especially foraminifera and radiolarians. These tiny organisms are highly sensitive to temperature and nutrient availability, making them ideal indicators of environmental change. Their widespread restructuring signals a deeper transformation in marine ecosystems, from surface productivity to the functioning of deep-sea food chains. This sets the stage for the remainder of the Palaeogene period, and beyond. The Oligocene was an epoch marked by gradual faunal turnover as life adjusted to cooler, drier conditions, and the continued expansion of grasslands. This ecological shift wasn't a sudden break, but a slow, ongoing transformation that carried on throughout the period. So, what marked the end of the Oligocene? Was there another extinction event? Actually, no. There were no extinctions significant enough to be called an event in the same way as earlier transitions. Instead, the close of the Oligocene, and thus the end of the Palaeogene period, was defined by environmental and ecological changes. In fact, it's difficult to point to any single moment or development that clearly divides the Oligocene from what came next. That said, there were some key trends. Antarctica became fully isolated and its glaciation intensified. The Himalayas and Andes continued their uplift, reshaping wind and weather patterns. The Tethys Ocean, once a vast tropical seaway, continued to shrink, closing off more shallow marine connections. The climate cooled further and became increasingly seasonal. Tropical forests continued to contract, while grasslands and savannas spread across large parts of the globe. These open habitats promoted the success of grazing herbivores, and with them came predators and competitors. Many modern mammalian families, such as dogs, cats, and deer, became more prominent. At the same time, older lineages like the hyaenodonts, a group of carnivorous mammals, and the anthracotheres, semi-aquatic relatives of hippos, began to fade away. And with that, we arrive at the end of not only the Oligocene, but the Palaeogene period as a whole. As Earth entered the Miocene, the first epoch of the Neogene, it had already undergone a profound transformation. In many regions, the tropical forests that had once blanketed the lands had given way to open woodlands and grassy plains. Animal life had evolved in response to the cooler, more seasonal world, laying the groundwork for the modern ecosystems we see today. These changes would prove to be just the beginning. The world's long-term cooling trend would continue, eventually culminating in the ice ages of the Quaternary. I hope you enjoyed this video. The Palaeogene is a fascinating chapter in Earth's history, often overlooked, caught between the dramatic fall of the dinosaurs and the rise of modern mammals. But it was a pivotal era, one that shaped the world's climate, ecosystems, and evolutionary path in lasting ways. Next week, we'll return to one of my more traditional videos, investigating a strange group of animals, the living invertebrates that are most closely related to the vertebrates. But for this extinction series, we'll continue our journey into the Neogene period to see what came next for life on Earth. Thanks for watching, and as always, let me know your thoughts in the comments below.